Hi everyone. In this video, we're going to go over in a little more detail the proof that consistency is sufficient for A-star graph search to be optimal. Before we get to that, I want to first address why admissibility, which we used in the case of A-star tree search, is not sufficient for A-star graph search. Let's recap that definition. An admissible heuristic, H, is one where for all states, the heuristic value is less than or equal to the true cost toward the end. Remember that a heuristic is an estimate of that true cost. Admissible means it has to be an underestimate. Now, it is not good enough for A-star graph search to be optimal. To illustrate this, we're going to see an example where A-star graph search returns a solution that is not the best solution. So let me draw that graph for you. We're going to have a start state, two states here, A and B, in the middle, and a goal state, G. Edges look like this. And I'm going to use an overly dramatic example just to illustrate the point. The cost on the edge B to G is 1,000, S to B is 100, and these are both 1. So clearly, the path that goes from S to A, then to B, G, is much better than the one that goes from S to B. Now you'll see in a moment why that 1,000 is there. Now we need some heuristic, and like I said, it needs to be an admissible heuristic. So at a goal, since the cost to get to a goal from the goal is 0, an admissible heuristic must be equal to 0. So we'll have H equals 0 at G. Now everywhere else, we're free to set the heuristic to be whatever we want, subject to that constraint. I'm going to choose H to be equal to 0 at all three of these. It's an underestimate, so that's fine. And I'm going to choose H to be equal to 1,000 right here. Notice that from A to get to G, you have to go from A to B, and then from B to G. So this is still an admissible heuristic. Now let's run A-star graph search and see what happens. Now that we're running a graph search algorithm, not a tree search algorithm, it's not enough for illustrating how this algorithm runs to simply draw the tree. We need to do that as well as keeping a closed set over here. Now remember that after we expand a node, we add it to the closed set so that if we ever take it off of the fringe again, we don't expand it again. So let's start. First thing we do is we add the start node, start state as the root node of the tree, and even though it doesn't make a difference, there's only one element in the fringe, let's check what its priority is. G equals, let me use a different color. G at this node equals 0, because remember G is the cost along this path, and this node represents the path from S to S. We haven't gone anywhere. So G is 0, and H, as I've defined it up here, is also 0. So F, the priority, is 0. We expand that node, add its children to the fringe, and we have A and B. Similarly, we need to figure out what the priority for both of these is. So G for A is equal to the cost of getting from S to A along this path. It's just 1. And H, as defined on the graph, is 1,000. So F is the sum of those two, 1,001. We need to do the same thing for B. The cost of going from S to B is 100, so that's G. And H of B is 0, so we have priority 100. Now, one last thing, since we expanded S, we need to add S to the closed set. To proceed from here, we need to take the one of these that has less priority, and that's the way that we order the nodes when we're expanding them for A star is whichever one of these has a lower f, and that's B. So we expand B, add its successors to the fringe. One of those is G. Now remember that we don't return a goal when we add it to the fringe, but only when we expand that goal node. So the algorithm doesn't terminate quite yet. But what does happen is, again, we add B to the closed set, and we need to compute the priority on this node. So G is the cost of going from S to B to G, which is 100 plus 1,000, 1,100. And H at G is 0, giving us a priority of 1,100, F value. Now that our two nodes on the fringe are S to A, with F equals 1,001, and SBG with 1,100, we're going to expand A next. So what happens when we do that? Well, we add its successors. We add it to the closed set. And then we compute its priority. Now notice, again, we don't check the closed set when we're adding things to the fringe, only when we expand a node. So the fact that B is already enclosed doesn't stop us from doing this. It's on the next step that we will realize that we aren't going to proceed in that direction. So G, S to A to B has cost 2, and the heuristic at B is equal to 0. That means F equals 2, much lower than the other one. So of course, SAB is the next node we're going to expand. The problem is, when we expand B this time, we notice that it's enclosed. So we do not add its successors to the search tree. We just stop exploring in that direction. And now the fringe is only this G over here. We expand that, see that it's a goal state, and return this node. And the path that we get is SBG. Up here, SBG. Clearly suboptimal. Cost 1,100 where there exists a path of cost 1,002. So what went wrong here? Well, it's a similar issue that we had with admissibility. Admissibility was a constraint that H had to underestimate the costs to get from our current node to the goal node, to a goal state. Now, we noticed that the first time we ran into B right here was along a suboptimal route, which means since we're using a closed set, if we later run into B along some optimal route, we won't continue searching down that branch. This is bad. So we want to consider a notion that is something like admissible for every intermediate goal. If we had something, a heuristic that was not only an underestimate for what it took to get from our current state to the goal, but also an underestimate of what it takes to get from our current state to B, then for the same reason that admissibility worked before, where the first goal we expand is the optimal goal, we'll now have a property that tells us more or less the first time we expand B will be along an optimal route. We'll make this a little more concrete in a moment. So I'm first going to give you a definition before showing you why this is exactly what we want. Consistency. Now, instead of comparing to the optimal heuristic, consistency is a property of one heuristic that compares this heuristic at one node to this heuristic at another node. So if we have two states, S and S prime, that are adjacent to each other, so there's an action you can take from S to get to S prime, then H of S minus H of S prime is less than or equal to the cost of traveling along that arc, S to S prime. This might be a little bit easier to visualize if I actually give you a piece of a graph. So imagine that we're working with a graph that has some node A right here, another node B right here, And somewhere over here we have a start state, some stuff happens, and we end up at A. And then some other stuff happens after B that gets us to a goal. All we are looking at right now, though, is this arc from A to B. So, in order for a heuristic to be consistent in this case, we would need the heuristic value at A minus the heuristic value at B to be less than or equal to the cost of getting from A to B. It might be a little more intuitive if we rearrange this equation a little bit. H of A is less than or equal to cost A to B plus H of B. For me, I prefer the top equation, although I found in my experience some people find the bottom one easier to conceptualize. Take a minute to look at them, clearly they're the same, but one way to think about this is that the amount that your heuristic decreases along any edge must be less than or equal to the cost of that edge. So if H of A is 8, and the cost of going from A to B is 4, then in order for this to be a consistent heuristic, H of B can't be any smaller than 4. Think about that for a moment. If it were smaller than 4, it would violate this constraint. One consequence of consistency, which we'll see in a minute is why we care about consistency in the first place, is that the F value along a path never decreases. Now, what do I mean by that? Consider a search tree. We always have S at the top, some other stuff over here, let's say D, C, and of course we'll have some other options. We're going to just look at one path for right now. And then A, B. You can imagine that this is a search tree for the graph we were just looking at with A and B. Now, what I'm saying is that anywhere along this search tree, this path going all the way from S down to B, F is going to be some value at S. Since G is 0 at the start state, you've incurred no cost so far. That's just going to be equal to the heuristic at the start. Let's say that's 8. And then F at D might be 9. F at C might be 9. F at A might be 11. F at B could be 12. But that F value, the sum of the cost and the heuristic, is never going to go down. Let me prove that to you really quickly. The first thing we need to do is just consider some arbitrary path P. Consider a path P. Now, a path is going to contain a sequence of states. So let's just call them, to be completely generic, S1, S2, dot, 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 ST minus 1, ST. So this is a path of length T. Now, what we want to show is that for any two adjacent states in this path, the latter one has an F value that's at least as big as the one before it. So we're going to now, within that path, look at SI and SI plus 1. We want to show that F of SI plus 1 is greater than or equal to F of SI. Now we're going to deal with some inequalities. Brace yourself. F of SI plus 1 equals H of SI plus 1 plus G of SI plus 1. So far, all we've used is the definition of f, which is just from A star search. It's the heuristic plus the cumulative cost so far. Now, because we know the path that Si plus 1 came from, it first went from S1 to Si, and then from Si to Si plus 1. So we'll bring that h down, but we can decompose this g right here to be the sum of the costs up to Si, which is GSI, plus the one remaining cost, which is cost of getting from Si to Si plus 1. Now, really important that you see this. GSI plus 1 right here, and GSI plus cost Si to Si plus 1, those are the same. We've just broken down this into two separate terms. Now we can actually use the consistency property that we have. How can we do that? Well, we know we have this guarantee about HSI plus 1, which comes from, let me actually write it again over to the side. Consistency says that the cost of getting from Si to Si plus 1 is greater than or equal to h of Si minus h Si plus 1. I've just switched around the order of the two sides of that inequality, but this is the same definition we had before. So, sorry, I should not have said we know something about HSI plus 1. What we can actually do next is something with this cost. So what can we do? Well, if cost is greater than or equal to this difference right here, then HSI plus 1 plus GSI plus that cost is greater than or equal to those same first two terms plus this difference, HSI minus HSI plus 1. You might see where this is going. Now what can we do? Well, we have an HSI plus 1 here minus HSI plus 1. Those cancel out. And we're left with this, GSI plus HSI. Remember the definition of F, that's just equal to F of Si. So you may need to go back over that derivation a couple times, but what we've just arrived at, this result, is FSI right here equal to this, greater than or equal to this, which is equal to this. So, as a final result, FSI plus 1 is greater than or equal to FSI. So, we now have, according to this proof, that the property right here, F value along a path never decreases, is true. What does this mean for us? Well, before getting into that, I just want to point out, really quickly, back in that example we looked at where the heuristic failed, the heuristic that was not consistent, did we actually run into a situation where the F value decreased? Yes, we did, and that's, in a sense, why we had this problem. Look right here. We have 1001 at A and 2 at B. Going forward in that path decreased the F value. And we can see that F equals 2, that really ideal node we would have liked to expand earlier, was blocked off, kind of walled by that one node in the middle where the heuristic was way higher than it should have been. So what's left? Now we need to prove that this property that consistency gives us increasing F costs along any path will guarantee that A star graph search returns the optimal path. When proving that A star tree search with an admissible heuristic was optimal, we used a diagram that looked kind of like this. So first, a triangle that represents the entire possible search tree. And up here we have a start node, S. Down here we have some suboptimal goal node, G. And we'll say there is an optimal goal node over here, G star. We're concerned about the possibility of expanding G before we expand G star. Now, if we draw the fringe to look like this, so we've explored everything up here, and now everything along this bottom line is what's on the fringe currently. We already considered the case where some ancestor n of G is on the fringe. And if that's the case, since consistency implies admissibility, I didn't go over that, but look back at it and convince yourself that any consistent heuristic must also be admissible, then that's going to be okay. What we're more concerned with now is if, for this n that we expect is going to be the node to save us because it will be expanded before G, taking us down to G star, what if instead of n, the state that is in n was also at another node n prime, which is suboptimal. So farther down, higher cost to get to it, but it's the same state, and we expanded n prime first. If that's the case, then even though we've guaranteed that we'll expand n before G, since the state in n is already in the closed set, since we already expanded n prime, we won't continue searching. It's a disaster. We failed to search, or at least failed to find an optimal solution. So here's the strategy. Let's consider some p that's above n. Okay? The particular p that we're choosing is whichever ancestor of p was on the fringe when we first expanded n prime. So if n and n prime are both on the fringe, since we said that n was optimal and n prime was suboptimal, we'd be fine. We know that n would expand before n prime, no problem. But if there's some ancestor of p on there, then we can actually show, similarly to before, that that's going to guarantee we'll get to n before we expand n prime. What do we do from here? Well, remember that n is a node where the path from S to n crosses through P, since P is an ancestor of n. So what that means for us is we already guaranteed that F costs are never decreasing along a path, they can only increase. Which means F of n is greater than or equal to F of P. Okay? How does that help us? Well, we can also compare f of n and f of n prime. Remember that f of n equals g of n plus h of n. F of n prime equals g of n prime plus h of n prime. N and n prime both have the same state, so these two right here are equal. So we're only comparing g of n and g of n prime. Since we said n is optimal and n prime is suboptimal, that gives us that g of n prime is greater than g of n. And therefore, f of n prime is greater than g of n. And as we saw right here, f of n prime is greater than f of n. And as we saw right here, f of n is greater than or equal to f of p. What does this mean? F of n prime greater than or equal to f of p. So p will be expanded before n prime. Follow that to its conclusion. When we're up here looking at p versus n prime, p will get expanded first, and we'll add something right here to the fringe, and now we're comparing those. And since that is either n or still an ancestor of n, that will be true there, and we'll keep going down until we end up with both n and n prime on the fringe. Once n and n prime are on the fringe, n will get expanded first because its cost is less.